So today we're diving into a fascinating paper called R&D-Agent-Quant, a multi-agent framework for data-centric factors and model joint optimization. Now, predicting asset returns in financial markets is, well, notoriously tricky. You've got high dimensionality, meaning tons of variables. Markets are non-stationary, always changing, and there's just inherent volatility. This paper tackles how current quantitative research pipelines often struggle with automation and coordinating different research components. So, this R&D-Agent-Quant paper proposes a solution using a multi-agent framework. This means it employs several specialized AI agents, kind of like independent workers, collaborating on the research. A key focus is on data-centric factors. These are variables like a company's price-to-earnings ratio that quantitative analysts use to predict asset movements. And for those interested in the implementation, the code for this work is in the QLib repository on GitHub. QLib is an AI-oriented quant investment platform, and it's now equipped with this R&D agent to help automate that research and development workflow. Alright, so actually gives us a nice visual of this whole quantitative finance research pipeline. You can see it's a cycle, starting with data acquisition and processing, which QLib helps with. Then it moves into factor research and development, in something called factor pruning, which is essentially selecting the most effective predictive signals and discarding redundant ones. Next is model training and model research and development. Then, importantly, there's market backtest, where strategies are tested on historical market data, another area where QLib assists. Finally, it loops back to financial analysis before starting again. Now, this R&D-Agent-Quant system automates those crucial steps of factor R&D, model R&D, and the financial analysis. Okay, so building on that overview from Mode, here gives us a more detailed conceptual diagram of the R&D-Agent-Q system itself. We can see it's an iterative loop, starting with an idea, then forming a hypothesis, moving to an experiment, and then into development where actual codes are generated. These codes are then put into a workspace implementation, and critically, there's a feedback step that informs the next round of research. What's highlighted here are two key optimization loops within the overall R&D-Agent-Q R&D factor, which is dedicated to improving financial factors, and R&D model, which is focused on refining the predictive models. The main R&D-Agent-Q system then orchestrates these. Alright, so after seeing those conceptual loops, here really breaks down R&D-Agent-Q into its 5 core functional modules and how they work together in that iterative cycle. First, we have the specification unit. This sets the stage, defining the task background, the data to be used, its format, and the overall mechanism for the quantitative investment strategy. Then, the synthesis unit takes over, generating new hypotheses, new ideas for factors or models, drawing from a kind of knowledge forest of past experiments. These proposed ideas become concrete tasks. Next, the implementation unit, which uses a specialized county steer agent, translates these tasks into actual factor codes and model codes. These codes are then evaluated and potentially merged into the pool of current SOTA, or state-of-the-art, factors and models. The validation unit then rigorously backtests these new factors or models using the QLib platform to see how they perform in simulated real market conditions. And finally, the analysis unit assesses these experimental outcomes. It looks at the strategy's performance and, this is quite clever, it decides the next action, like whether to focus on refining factors or models by framing it as a contextual two-armed bandit problem. This is a decision-making strategy that helps balance exploring new ideas with exploiting known good ones, using an algorithm called contextual linear Thompson sampling. This whole process then feeds back, creating that continuous loop for improvement. Okay, so we just talked about the implementation unit and its county steer agent. Here gives us a closer look at how that county steer workflow actually operates. It's really about two agents working together, a scheduling agent and an implementation agent. The scheduling agent starts with a list of candidate tasks, say tasks A, B, C, and D. It then learns to prioritize these, considering things like task complexity and dependencies, and creates an updated schedule. For instance, it might decide to tackle task C, then D, then B, then A. This schedule then goes to the implementation agent. This agent tries to execute the task, learns from any errors or feedback. For example, if a piece of code has an attribute error and uses this experience to refine its approach. This feedback also loops back to the scheduling agent, influencing future scheduling decisions. It's a co-evolving process, building up a practical knowledge base. Alright, so we've seen how County Steer helps implement tasks. Now it gives us a visual on the ideas themselves, specifically within the R&D factor component. This is a factor idea similarity landscape, shown as a heat map. It uses something called cosine similarity, which is basically a measure of how alike different factor hypotheses or ideas are. The brighter yellow areas mean the ideas are very similar. You can see these black boxes highlighting clusters of similar ideas across different experiment loops. The numbers, like 1, 2, 3, and so on, represent these loops or iterations of research. And those red numbers, they indicate factor ideas that were actually selected into the state-of-the-art factor library, meaning they were successful. This really shows how R&D factor explores different concepts and then refines them. Okay, so after seeing how R&D factor explores ideas, here shows us the bottom line, the actual experimental results. These tests were run on the CSI 300 dataset, which tracks 300 large cap stocks in China. The table looks at factor predictive power, like information coefficient or IC, which tells us how well the factors predict stock returns, and strategy performance, like annualized rate of return or ARR. And the R&D-Agent-Q framework, particularly the O3 mini version, really shines, achieving an IC of 0.0532 and an ARR of 14.21%, outperforming the other models and standard factor libraries. So building on those impressive overall numbers from here gives us a year-by-year breakdown of the information coefficient. Remember, that's how well the factors predict stock returns, specifically for the R&D factor component. We have two charts. Chart A shows R&D factor when it's initialized with a basic set of factors called alpha 20, and chart B is when it starts with a more complex set, alpha 158. Both compare against standard factor libraries. What's really interesting is how the R&D factor lines, particularly the purple and brown dashed lines representing different LLM backbones, tend to hold up or even improve their IC values by 2020, while some traditional factor sets show a decline. For example, in chart B, R&D factor, initialized from alpha 158, clearly surpasses the baselines in 2020. This really highlights its ability to adaptively refine and find strong predictive signals. So that year-by-year improvement we saw really highlights the core strength of R&D-Agent-Quant. The main takeaway is how this multi-agent system can discover and then dynamically refine financial factors, outperforming traditional methods. It's a big step for data-centric AI in finance, potentially leading to more robust and adaptive investment strategies. That's all for this AI Research Roundup. Thanks for listening. I'm Alex.